Our next speaker is Dr. Wei-Hsiang Shao from the Center of iTHEMS at RIKEN. He's going to tell us about what happens when scale separation fails in physics. Let's welcome Wei-Hsiang.
Yes, I would like to thank the organizers for the support, the hospitality, and for giving me the opportunity to present here. This talk is based on a series of work done in collaboration with this list of collaborators, including Professor Pei Ming and also Zhi Hao, who I think is in the audience. So I would like to start by showing what Alvaro showed yesterday, which is some of the important scales and important energy scales in particle physics. And one remarkable property feature of this is that there is an enormous separation of scales. So for instance, there is a 17 order of magnitude difference between the Planck scale and the electroweak scale. And there is a 61 order of magnitude difference between the Planck scale and the cosmological scale. So as you know, the Wilsonian framework of effective theories takes advantage of this scale separation. So suppose that we have our theory contains some UV scale lambda, and we are only interested in energy scales E that is much less than lambda. Then what we would usually do is to integrate out the UV degrees of freedom larger than lambda. And if the UV theory is local, what happens is that the UV effects on the observable A, for instance, would come in a derivative expansion, which is analytic in energy E. And so the Wilsonian framework basically tells us that if we want to describe phenomenon at some energy scale, we just need a corresponding effective theory at that energy scale. And the effects of UV physics come in finite number of Wilson coefficients. And the effects are also suppressed due to scale separation. And this is also the reason why, for instance, people working on quantum computers don't have to worry about quantum gravity, even though quantum gravity is acting on the quantum computers. And moreover, based on intuition from local quantum field theory, usually we would prescribe a distance scale L, which is associated with the energy scale by this inverse relation. So for instance, for a relativistic probe with energy E, it has wavelength E inverse, and it can probe distance scale L of order E inverse. So for instance, the Planck scale corresponds to 10 to the minus 33 centimeters. So this is the conventional story. But as mentioned by Professor Levine, gravity provides a simple example why this intuition cannot be extrapolated all the way above the Planck scale. So as I mentioned, to probe a distance delta x, we need a particle with energy E inverse delta x. But in the presence of gravity, this energy itself gravitates. So for instance, when there is a sufficient amount of energy localized in a sufficiently small region of space-time, there's another scale that comes into play, which is the Schwarzschild radius, 2e. So when the energy E is small, we can still improve our resolution by increasing the energy in the usual way. But at around the Planck scale, where these two lengths are comparable, we end up creating a black hole of size Planck length. So this black hole obstructs us from accessing that region. And if we increase the input of energy, we end up creating a larger black hole of the size of the Schwarzschild radius, of the Schwarzschild radius. So in this example, we see that if we go to the UV limit where E becomes large, we actually end up probing the IR distances where delta x is large. So this is known as the UV-IR correspondence in gravity. So this is one reason why sometimes you hear people say that space-time is doomed, meaning that the notion of space-time below the Planck scale breaks down because the act of probing that region actually creates a black hole, which forbids us from accessing that region. And so, but there have been several proposals that attempt to incorporate such a UV-IR behavior into quantum mechanics. So two most well-known ones are GUP, Generalized Uncertainty Principle, which I will explain later, and also the space-time uncertainty principle, which I will also explain if there is time left. So let me first start with models with UV-IR correspondence. And here, by UV-IR correspondence, I mean that somehow UV physics introduces a new IR distance scale. So let me start by introducing a simple model for GUP. And so we can consider a one-dimensional quantum mechanical model. And the difference is that the position operator X, which was originally I del P in momentum space, is now modified to be 1 plus L squared P squared. And in order to keep this position operator symmetric with respect to some inner product, the measure of the inner product should receive this type of correction in the denominator. So as you can see, based on these representations of the position and momentum operators, using the usual uncertainty relation, so the commutator between X and P is 1 plus L squared P squared. So this uncertainty principle would give us 1 plus L squared times the average of P squared. And this can be written in terms of the uncertainty and the average of momentum in this way. So the first term is the usual Heisenberg uncertainty relation. It represents the wave nature of particles. So if you consider a state with a large spread in momentum P, it is localized. It can be very, very well localized in position space. But here now we have these type of new correction terms, which says that now when you have large momentum, you can actually not localize it. So there's a competition between the usual term and the correction terms. And this is basically due to motivation from string theory considerations. So we can study this uncertainty relation in a bit more detail. So suppose that we fix the mean momentum of the state. We fix P expectation value of P, then we can try to minimize delta X with respect to some delta P. So what one would find is that for a fixed mean momentum, the minimum uncertainty that we can achieve is given by this quantity. So Planck length L times square root 1 plus L squared P squared. So this is larger than or equal to L. So this means that this basically says that there is a fundamental length scale L, which sometimes people understand it as the string scale. And furthermore, there is a UV-IR relation where if we go to the UV limit where P goes to infinity, this length scale also goes to infinity. So as usually in quantum mechanics with the usual Heisenberg uncertainty relation, we can obtain the minimum uncertainty wave packet, which is a Gaussian. And we can do the same thing with GUP. And this wave packet, I will call it psi px. So P means the average of the momentum, and X means the center of the wave packet. So I call this psi px as a function of X. So this wave packet, this minimum uncertainty wave packet is no longer a Gaussian, and its width in position space obeys this relation. So as you can see here, so we have P3 larger than P2 larger than P1. So P3, the wave packet for P3 is more spread out, and the wave packet for smaller momentum is more localized. But this is basically saying that if you have sufficiently large momentum state, it cannot be localized due to this GUP effect. So physically, this implies a very interesting phenomenon, which is suppose that we consider some background potential in our quantum mechanical system, which I call Vx. And suppose that this potential has some characteristic width W. which I assume is much larger than the Planck length, then usually we would expect that if we want to probe this structure, this potential structure, we would need to send in a particle with momentum larger than W inverse. This is the usual story. But now under GUP, it turns out that we also cannot make the momentum too large compared to this critical momentum PC, which is defined to be W divided by L squared. And the reason is the following. So if P is much larger than PC, then this minimum uncertainty relation tells us that delta X is very large. So if you send in a very large momentum probe, now it has a very wide width. So it has a very broad spatial extent to the point where its spatial extent is much larger than the width of the potential. So you can no longer resolve the potential. You can no longer probe the potential. So this is something like, so if you consider phonons in condensed matter system, if the phonon has sufficiently large wavelengths, long wavelengths, then you don't have to care about the microscopic details of the condensed matter system because the atomic structures are smeared. And similarly, if you consider cosmological spacetimes, on cosmological scales, you don't have to worry about local inhomogeneities such as black holes and galaxies. You can just approximate the black background as being homogeneous and isotropic. So similar things happen here. It's just that now, for a sufficiently large momentum state, the background is also smeared. So this introduces a notion of scale-dependent geometry, where the background depends on the energy of the probe. So here's an explicit example showing this phenomenon. So here I define the effective potential as a function of the center of the wave packet and the mean momentum of the wave packet. This is simply the expectation value of the background potential observed in the minimum uncertainty wave packet state psi px. And it is defined using the usual quantum mechanical prescription in this way. And this is a plot. So suppose that the background potential is a Gaussian barrier, V of x, with width W and height V0. Here is a plot. The horizontal axis is momentum divided by the critical momentum PC. And this blue line is the center, the height of the effective potential divided by the height of the original potential. So you see that once the momentum exceeds the critical momentum, the height of the potential decreases rapidly because the potential is smeared. Perhaps this is a better representation. So this dotted line, this dashed line is the original Gaussian barrier. And the other lines are the effective potential viewed by a wave packet with these respective central momentum values. So as the momentum of the state increases, the potential is more and more smeared. And in fact, so this says that for a very high energy state, it essentially sees no potential at all. And even though this is a static, so this is just the instantaneous profile of the potential, we can also study how the scattering, how the probe with momentum P scatters off this potential. And you will also find that the reflection coefficient is suppressed as we go to larger and larger momentum. So basically saying that the very high energy probes see no potential at all. Okay, so that was the GUP part, and there's also this space-time uncertainty relation, but if there is time, I will come back to this. So now let us try to apply what we just obtained to black holes. So as you may know, black holes would, even though classically black holes are purely absorptive, quantum mechanically, it is believed that black holes would slowly lose its mass by emitting Hawking radiation. So suppose that the size of the black hole, which I call A, is much larger than the Planck length, which I assume to be much larger than the Planck length, then the conventional lifetime of the black hole scales as A cubed. And if you put back the units, you would find that for a solar mass black hole, the typical lifetime is 10 to the 67 years. So this is much longer than the current age of the universe, which is 10 to the 10 years. But this is still finite. And this is what people usually believe based on low energy effective theory. However, if we take a closer look at how Hawking radiation is produced, we find that they are produced in a way that exhibits also a UV-IR connection. So here, this is a space-time diagram of a black hole. The vertical direction is time, horizontal direction is radial distance. And this is the collapsing matter. So before matter collapse, we have Minkowski space, and this is the trajectory of matter. And after the matter contracts to within its Schwarzschild radius, r equals a horizon forms, and the space-time here is a black hole space-time. And suppose that we have some Hawking particle represented by a low energy wave packet. And what happens if we trace it backwards in time is that due to the strong gravitational field near the horizon, as we trace this wave packet backwards in time, its wave fronts are compressed. So as you can see by these trajectories, so the wave fronts are compressed. So this wave packet is blue shifted as we go backwards in time. So this low energy wave packet is actually originated from very high momentum wave packet in the infinite past. And how large is this momentum? So suppose that the frequency in the future is omega 0 at time u0. Then the frequency in the past is exponentially large in terms of the time. And in particular, we see that this low frequency Hawking particle is produced from very high frequency modes in the past. And in particular, after some critical time scale, a log a, the ancestor frequency p becomes larger than Planck scale. So this basically means that this black hole space-time connects UV to the IR. And this has nothing to do with the black hole singularity. This is purely a consequence of this black hole space-time outside the horizon. So black hole is an arena that breaks scale separation. Right, so the red line is basically the geodesics of outgoing light rays on this spacetime. So this spacetime is not the Penrose diagram, so they are not 45 degrees. So in the Minkowski space, this is the trajectory of an outgoing light ray. And in the black hole spacetime, there is this exponential redshift, so it's going to approach the horizon exponentially. That means particle looks something. Not really, because this energy is so maybe I should show the equation, but the point is that outside the black hole spacetime, the momentum is not conserved. It's not a conserved quantity. Only the frequency, the killing frequency is a conserved quantity, but the momentum is not. So as you go backwards in time, the momentum increases. So maybe this is a clearer equation. So I don't derive this, but this is basically you can just understand this as the outgoing Klein-Gordon equation on this spacetime. It takes this form in VR coordinates. So the effect of the black hole comes through the right-hand side. So this term can be viewed as background interaction term. And this A over R can be viewed as the potential, the background potential in this scenario. So suppose that we incorporate GUP into this setup. So what we do is we simply deform the position in momentum space by adding this deformation. So immediately we see that because R appears in the denominator, by adding this deformation, the essential effect is that the Schwarzschild radius A is now turned into a scale-dependent quantity, A effective, which is a function of P. So it takes this form. And in particular, in the UV limit where P goes to infinity, the effective Schwarzschild radius goes to 0, which means that the background interaction goes to 0, which means that the Transplanckian modes with very large momentum essentially see no black hole at all. So what are the consequences on Hawking radiation? So originally, as I explained, Hawking radiation at late times, by late time, I mean after A log A. Usually, this late time radiation is produced by the Transplanckian ancestor modes interacting with the black hole background. This is the usual story. But now under GUP, as we saw in the previous slide, the black hole is invisible to Transplanckian modes because Transplanckian modes see an effective Schwarzschild radius that goes to 0. So so actually we found that Hawking radiation is also terminated after this critical timescale a log a. So just to give you a number of how this timescale, how large is this timescale? So for a solar mass black hole, a solar mass black hole, the size A is around a few kilometers, and L, the Planck length, is 10 to the minus 33 centimeters. So this is actually a few milliseconds. So after the black hole starts radiating, after a few milliseconds, the Hawking radiation is stopped. And because this is such a short time, the mass loss due to Hawking radiation is also negligible. So actually, we found that under GUP, we can realize something like a large remnant of a black hole. So this is also another way how you can understand why Hawking radiation is terminated. So here is again a space-time diagram. The vertical direction is time, the horizontal direction is space, and this is the world volume of black hole. So here, this is a very zoomed out scale. So if we zoom in here, this is matter collapse forming a black hole of size A. So as I explained when introducing GUP, so for Transplanckian modes with momentum much larger than the critical momentum PC, which is now defined by A over L squared, since A is the characteristic width of the black hole. If P is much larger than PC, then based on GUP, these states are very extended. So they have an uncertainty in the X direction that is much larger than the size of the black hole. So this is why they don't see the black hole, because the black hole is smeared. So just as the quantum mechanical example, the potential is smeared for very high momentum mode. Here, the black hole would also be smeared by a very Transplanckian mode. So this is a representation of this. So this extension in X direction is much larger than the size of the black hole. So the evolution of such modes don't see the black hole. They evolve according to the asymptotic geometry instead. And this is why Hawking radiation is terminated, because such a modes don't see the black hole. So they don't participate in the Hawking radiation process. Okay, so I just have 5 minutes, but okay, so let me just briefly go through the other model with UV-IR connection, which is space-time uncertainty. And space-time uncertainty can be realized by non-commutative field theory. And because due to time limit, the only thing to know for this talk is just that non-commutative space-time is equivalent to deforming the product of ordinary functions with commuting coordinates by this exponential operator, the star product. And so for instance, this is some type of non-commutative field theory where the interaction with the background potential is deformed by this star product. And we can do the similar thing as we did with GUP. We can define an effective potential, and you see there's some interesting shift behavior. But again, we can also make the same argument that as the momentum becomes very large, the background potential becomes more and more smeared. So we can also apply space-time non-commutativity to Hawking radiation. And so this is a plot. Vertical direction is the size of the black hole as a function of time. The horizontal direction is time. So in the ordinary case, based on Hawking's original calculation, the black hole evaporates completely within a finite time scale, which scales as a cubed. And as we saw in the GUP example, once we include GUP, the black hole, the Hawking radiation terminates after some time. So the black hole never evaporates completely, and we have large remnant. And actually, what we found by incorporating space-time non-commutativity is that the black hole ends up still evaporating away, but the evaporation time scale is enhanced by exponential of a squared over L squared. So for a solar mass black hole, A is around a few kilometers, L is 10 to the minus 33 centimeters. So A over L is 10 to the 38. A squared over L squared is 10 to the 76. So this is e to the 10 to the 76. And words cannot describe how large this is. So, but in any case, it is much larger than the conventionally believed evaporation scale. So here is the summary. So basically, it has been known that some non-local models inspired by string theory feature uncertainty relations that show some type of UV-IR correspondence, where there is some new scale L that is proportional to the momentum P, such that if we go to the UV limit where P goes to infinity, this new length scale also goes to the infrared limit and becomes macroscopic. And our contribution is that we apply this framework to the black hole setting. So although this length scale becomes macroscopic only in the UV limit, we found that they can nevertheless lead to large effects on naively low energy observables such as Hawking radiation. So we found that by incorporating these effects into the calculation of Hawking radiation, we find that opposed to conventional belief, there can actually be order 1 effects. So thank you very much.
Other questions or comments?
Repeat in the toy model that you introduced, the first one. Could you? Is there any motivation to add L? Like yeah.
This one?
Yes.
Yeah, so the original motivation is just to realize something like this type of uncertainty relation. So originally, this type of uncertainty relation was conjectured by people studying the high energy scattering of strings. So when you investigate the string scattering amplitude at high energies, you find that you can do a saddle point approximation, and the resulting saddle point configuration of the worldsheet sort of exhibits this feature of a larger extension that is proportional to the center of mass momentum of the incoming strings. So this is a relation that people conjectured, and these gentlemen try to realize such an uncertainty relation by considering such a deformation in a quantum mechanical model. So obviously, this is still some type of effective theory, but nevertheless, it can capture some interesting UV-IR behavior.
So also, could you get this in non-local theories with non-local interactions? This is what you mentioned at the end.
Yes. So in principle, so this is sorry. So as you can see, so this is some type of non-locality. So this is also, these are all non-local theories. So for instance, if you look at so for instance, in this non-commutative field theory, this is a non-local operator. And in this, so in this GUP, if we deform R by this type of deformation, you also get some sort of non-local theory.
Okay, thank you.
So non-locality is very important here.
The question?
Yeah, so what happens if you do this kind of calculation within conventional string theory?
Oh, this type of Hawking radiation calculation.
Yes.
So that's our ultimate goal. But unfortunately, so right now we don't have string theory on curved spacetime. So, but one good property of this collapsed geometry is that within the collapsing matter, we have flat spacetime. So in some of our recent works, we have tried to incorporate stringy effects into this flat space scattering between these stringy modes with the infalling matter. So in that sense, we could sort of get closer to our ultimate goal. But as you said, indeed, ultimately, we would like to treat all of this as a sort of a scattering process involving the black hole as well.
Does imposing this generalized uncertainty principle also
give some physical consequence on the information paradox.
Right. So that's a very good point. And so as you can see from this figure, so usually information paradox is associated with the fact that conventionally people believe that black holes would simply evaporate away. So under GUP, if Hawking radiation is terminated after a certain time, the black holes would not evaporate away. So the information is contained inside the black hole. So in this sense, the information paradox is resolved.
So I have a practical question. So if LHC create a black hole, will live longer, not evaporate?
So that's a very interesting point because so it depends on what is the size of the black hole that LHC is able to create. So for instance, here in our calculation, we are always assuming that the size of the black hole is much larger than L Planck, the Planck length. So that would give you this picture. Now, if you end up creating a black hole that is very small, very close to the Planck size, then our calculation doesn't really work because semi-classical gravity breaks down. But at that scale, so some people in quantum gravity already proposes microscopic remnants. So people also propose that once the black hole evaporates down to Planck size, it would stop evaporating.
So should we be worried?
Not really, because Hawking radiation is, as I explained here, Hawking radiation is a very weak effect. So these are simply like this is simply like very low energy radiation. So if it stops, it's just nothing dramatic.
And can you understand and the GUP are in a completely general covariant way?
Yes, so that's an interesting question. So indeed, some people have proposed a covariantized version of GUP, but here we are treating it as some sort of effective theory. So, and in particular, in the case of black holes, the collapsing matter chooses a preferred frame. So, yeah, but you are right. If you take it as a fundamental theory, then you should covariantize it, and people have done that. But for our purposes, we can simply take it as a modification in a preferred frame. Yes. Yes, so if you take, this is the Vidya frame. So if you go to 3D falling frames, we have checked that the result also the same.
So I decided so.